In this video, we're testing the convergence of the series 3 over n squared minus 2. And we're going to use our previous knowledge of p series to get this done. So remember, for a p series, and the starting point doesn't really matter here, it's the tail of the series that determines whether or not it's going to converge. For a p series, we normally wrote it like this. The sum as n goes from 1 to infinity of 1 over n to the power p. And we've already proven that this thing is going to converge if p is greater than 1 and diverge if p is less than or equal to 1. So let me point out first that the 3 is not even relevant to the question here. Every term in that series has a 3, so we could just factor it out in front. That's not really the essence of the problem. So I have the sum of these terms that look like 1 over n squared minus 2, and a meaningful direct comparison to the convergent p series 1 over n squared is not possible here. I'm subtracting 2 in these denominators, and making the denominators smaller makes the fraction bigger. So these terms are actually bigger than the terms of 1 over n squared, and being larger than the terms of a convergent series doesn't prove anything at all. What we need here is to capture the essence of these terms by using a limit comparison. So I'm thinking to myself, when n becomes large, the minus 2 is negligible, and this series essentially becomes 1 over n squared. That's what the limit comparison test is usually about. So we're going to limit compare to the convergent p series, again, just using a prior result about p series, 1 over n squared, because when I glance at the series that we're studying, I can tell the essence of its behavior is 1 over n squared in the large n limit. So what we do is we take the limit as n goes to infinity of the ratio of the terms of our two series. And I'm not even going to include the 3 in this. So I have the terms in the series that I'm studying, 1 over n squared minus 2, divided by the terms of the series that I'm limit comparing to. Well, dividing by 1 over n squared is the same as multiplying by n squared over 1. So there's the limit I have to compute. If it turns out to be a finite number, then I know the two series are going to share their convergence behavior. So I end up with the limit as n goes to infinity of n squared over n squared minus 2. Now, as a physicist, I'm just going to say, oh, the minus 2 is negligible when n becomes large. And I end up with the limit as n goes to infinity of n squared over n squared, which is 1. And the limit of 1 is just 1. We arrived at a finite constant in the limit comparison test, so I know that both of our series converge. And really the point is, you want to be able to do this at a glance. You want to go back into this original series and say, oh, the 2 is negligible in the large n limit. This is basically a 1 over n squared thing. I know it's going to converge. Now, for those of you forced to show a few more steps in your introductory calculus classes, we can pretend to be a little more rigorous here, instead of crossing out the negative 2, by dividing the numerator and denominator by n squared. And I'll explain what I mean about the deception here. So we're going to divide the top and bottom by n squared. I end up with a 1 over 1 minus 2 over n squared. At this point, you're usually allowed to go ahead and say, oh, when I take the large n limit of 2 over n squared, that gives me 0. This reduces to the limit of 1, which is just 1. Now, the deception that bothers me here, and the reason I allow my students to use this more casual approach, is that in introductory calculus, you usually haven't even proven rigorously that the limit of 2 over n squared goes to 0. So this added work here is really pretending to be logically rigorous when there are still holes in the logical argument. And I think if we're just going to be semi-formal anyway, and we have a method that always works, in other words, crossing out the negligible terms, let's use the most efficient method. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.